Hi, in this video I'm going to briefly go over some of the concepts covered in Chapter 13 about sample size and power analysis. So why do we care about sample size and planning this when we're developing a research study? Well, sample size is really important because studies that are too large waste resources and may unnecessarily expose subjects to risks, inconveniences, and burdens with limited additional societal benefit. However, studies that are too small are underpowered, leading to findings that might be invalid, misinterpreted, or never disseminated. So the basic principles of statistics can be used to calculate a justifiable sample size for a study. And the process often requires researchers working in collaboration with a statistician to consider many other important matters. I always work with a biostatistician when I'm planning a study and writing a grant and need to come up with my sample size. Although the final sample size for a study is often affected by the availability of subjects, financial resources, and ethical considerations, sample size calculation is a necessary first step to balance statistical needs with issues of feasibility. In general, sample size calculations are typically based on type 1 and/or type 2 errors. Alpha refers to the probability of a type 1 error, sometimes called the level of significance or the significance level. So it's the probability of rejecting the null hypothesis when it is in fact true. Whereas beta refers to the probability of a type 2 error or the probability to fail to reject the null hypothesis when it is false. Power analysis is used for sample size calculation for hypothesis testing studies where a researcher uses a predetermined alpha and attempts to achieve a desired level of beta, or conversely power, by choosing a sample size to detect some clinically or scientifically meaningful effect. So here, power is defined as 1 minus beta, and so it refers to the probability of correctly rejecting the null hypothesis when it is false. Before covering the details and mechanics of power analysis, it's important to stress the critical point of assuring consistency of sample size estimation and the data analysis plan. The implications is that it is extremely important for the research team to carefully consider their study design, the measurement of their primary endpoint, and their proposed data analysis plan before attempting a power analysis. There are 6 pieces of information that are outlined in Chapter 13 that are necessary in order to compute sample size using a power analysis. The first of which is knowledge of how the primary endpoint is measured. So measurement of the primary outcome of the study drives the selection of the statistical method used to analyze the data, which is necessary to know when conducting a power analysis. 3 broad categories to consider include discrete responses, most common is dichotomous or binary responses such as dead or alive, continuous responses like cholesterol levels, and time to event responses, so time until the occurrence of an event. Next is the type of hypothesis test proposed. Tests for difference, also called test for equality and test for equivalence, are two-sided or non-directional, whereas tests for superiority and non-inferiority are one-sided or directional. Go back to Chapter 9 to review this if you have forgotten or you aren't familiar with that. Some controversy concerning one-sided tests versus two-sided tests, especially with respect to tests for superiority versus tests for differences. Two-sided tests are generally preferred and used in the biomedical literature. However, that being said, non-inferiority trials are becoming increasingly common due to increased emphasis on comparative effectiveness research. The next piece of information that you should consider is the measure of variance or precision. So in general, a more precise method of measurement, in other words, smaller variance, will permit the use of a smaller sample size. Thus, as statistical variability increases, the sample size needed to detect an effect also increases. With continuous outcomes, this parameter is usually represented by the population standard deviation, whereas with dichotomous outcomes, it depends on the proportion of the event in the control group and the increase or decrease in the proportion having the event in the treatment group. Some special considerations have to do with regarding the reliability of measures and whether or not you are going to be doing repeat measurements. magnitude of the effect, also called the effect size, it reflects a clinically or scientifically relevant treatment effect that the study should be able to detect. The difference between two population means or proportions in the case of a two-group problem is an example. All other things being equal, the necessary sample size increases as the size of the treatment effect decreases. Choosing this parameter should be based on clinical judgment, experience, and expertise, not statistical considerations. Some special considerations to think about are the use of standardized effect sizes such as a Cohen's d, and that go back to the textbook to read about that. Next, you have your specified significance level. Alpha is chosen by researchers early in the study planning period. Conventionally, it's set to alpha of 0.05, although other values are possible, such as 0.01 or 0.1. All other things being equal, the required sample size for a study increases as the probability of a type 1 error decreases. Or stated differently, one way to increase the power of a statistical test would be to increase the probability of a type 1 error one is willing to accept. And lastly, we have the target level of power. So as with alpha, power is also set in advance by researchers. Its conventional level is 80% or 0.8, although recommendations for power of 90% are becoming increasingly common. All other things equal, sample size requirements increase with increasing target levels of power. So in general, the required sample size for a study increases with increasing variance. So if you have increased variability within your group, you're going to need more subjects in order to detect that true effect. Your sample size will increase with decreasing probability of a type 1 error, and your sample size will increase with increasing desired target level of power, and will decrease, sample size will increase with decreasing size of the effect of interest. So besides these 6 pieces of necessary information, there's also a multitude of additional considerations when calculating sample size. And some of these include the use of paired observations, for instance, a pre-test, post-test design with no control group or a crossover design, usually requires some information about the correlation between the measurements. The use of interim analyses of accumulating data in a clinical trial also requires a statement in the protocol of the number and timing of planned interim analysis monitoring and the interim monitoring method, because all 3 of these can affect the initial sample size estimate. Investigators may elect to enroll a larger number of subjects than suggested by the sample size calculation to account for potential loss to follow-up. And other considerations include whether there are multiple endpoints or whether subgroup analyses and statistical tests of interaction will be performed. In addition to these, investigators performing sample size calculations also may need to consider the implications of the following topics, and you can go back to the textbook to read more about these. Case control and cohort studies, determining variance, sample size estimation for more complex analyses, retrospective power analysis, which I will tell you right now, I don't want anyone to be ever doing that. There's a lot of debate with it, and if you read in the textbook, there's not much utility to it. And then finally, sample size planning using precision analysis. So in summary, sample size calculation plays a critical role in the planning stage of a study. The primary approach used in this chapter and what we've covered involves a power analysis, but the use of precision analysis is also demonstrated. And to understand what that is, you can go back to the textbook, but it's more about an estimation. Choosing an effect size of interest and a standard deviation or variance in a power analysis are often the most difficult tasks in sample size planning. Other considerations may influence the calculations and the final sample size estimate. Careful attention to these matters, including the prescription to avoid retrospective power calculations, is important. And lastly, I just want to say that there are some worked examples using G-Power in Chapter 13 of your textbook, given different types of study designs and types of analyses with screenshots. Please review those. I think they're a good resource to kind of show you how these programs are used to select sample size.